This will be a description of adapting a conventional table loom with a Dobby head. In this particular case, I'm using an 8-shaft 24-inch Ashford table loom. It kind of stops here. What I've added is the Dobby head. And I really haven't modified the structure. The way this one works is when you pull a lever, the cords go down, pull the white cords, and the appropriate shaft raises. I've really played off that same mechanism. In this case, what I've added is a motor connecting rod, and I've actually used a black string here for contrast, so that as the motor turns, the thread is picked up on the blue taped area here. As the cord winds around the shaft, it then pulls the shaft up. So as I actually activate it, it's going to raise the indicated number of shafts as controlled by the software. So that will change each time I hit a new shot. So that's the basic mechanism, and then the electronics are actually mounted in here, and I'll get into that in more detail. And then a lamp on top, simply so that you can see what's going on. Now, I don't want to make this too specific to this particular loom. Let me talk about the key parameters that you need to know to get there. One of the first questions is what kind of motors you need. In this particular case, let me just raise all the shafts for the moment. I've got a simple little kitchen scale. I'm going to set it on the rail. When I release the shafts, all the weight of the shafts is now sitting on that scale. Measured in metric, since it's going to be easier to look at that from the way the motors are specified, I've got about 2.6 kilograms. And what I'd actually done when I had a warp on this is if I then raise that scale to the top, I can actually see what total force required on the motors would be with the loom tension on it. So approximately double that. So I've now got an idea how much weight I'm trying to raise. That determines motors. This is a little NEMA 17, which is a 1.7-inch motor, and I'll talk more about exactly how to determine that. But once I know the motors that I'm using, I know the shaft, I can then measure those kind of connections. And those physically are going to sit on a sidewall, so the motor simply goes through, sit on those connections, and turn the shafts. And again, I'll talk about that in more detail. The other thing that is interesting to know while I'm on the loom is how far apart the shafts are. So what I actually did was just take a small ruler, measure from the hole on the first shaft to the hole on the last shaft. It was about 3 inches. Divided by the 7 gaps between the shafts gives me about 0.4 of an inch per shaft. And so that gives me the basic parameters I need in order to try and determine what's got to happen at the next stages. Now let me zoom in a little bit on the side there. Okay, this is a little bit more of a side view, so you can see a little bit more. Again, the motors connect. This connects the long rod to the motor shaft. The tape here is just to increase the diameter so that it takes less rotations to pull the string up the desired distance, and that's just a function of speed. And that turns out to be a trade-off between the motor torque and the speed to move it. And we'll talk that in more detail. The little collar here simply holds the end of the cord, and then you can see where the cord goes just through one of the feed holes, the same hole the original cord went through. And there's a small, slightly oversized knot that just loops over the screw at the end of there. So in order to disconnect the whole Dobby head, all I have to do is unhook 16 of those, 2 on each shaft, and take out a butterfly nut that's sitting here that holds the overall Dobby mechanism to the castle of the loom. And then the whole thing lifts off. In order to put it back on, same thing, 2 screws, and I usually use a twist tie in order to go around the end of the loop, feed it through the hole. And the only modification of the loom is on this side rail. There's one small hole in the corner here, which is where the bolt goes through, so that when the Dobby head is gone, there's very, very minor modification to the loom. It's right next to another hole that's already on the loom, so I'll talk to that again later. Okay, let me talk about stepper motors here for a couple of minutes, since that's going to be the first issue we got to deal with. Now, if you look at the weight we saw a few minutes ago, it's 2.6 kilograms for the full collection of shafts. At 8 shafts, that works out to about a half a kilogram per shaft. Now, when I look at the lever arm, I cheated a little bit looking at the motors we're going to deal with.
It's a 5mm shaft, and I've got about a 1mm cord that I'm going to deal with. I then want to increase the diameter so I can make things a little bit faster. And so I've got 12 inches of blue tape on there. Gives me a net about a 10mm shaft diameter, which gives me half that, or 5mm or 5 centimeters for the lever arm. So the torque then would be the 0.6 kilograms times a half a centimeter. So theoretically, it should only take about 0.3 kilogram centimeters to lift a single shed. And theoretically, that should be under tension. Now, what you're going to find out when you start looking at stepper motors is they tend to be specified by holding torque. And that's not the dynamic lifting power, so it can't move that much. Now, empirically, I've kind of found there's almost a 10-to-1 factor there between the holding torque, think of that like a brake, and what it takes to actually move it. So I'm looking for a motor in the approximately 3 kilogram centimeters or 30 Newton centimeters. And just for the sake of this project, I was looking for a ballpark of about $100 target project. And for 10 motors, I'm looking $5 to $10 per motor to give me a price range. So nominally, I'm looking for a NEMA 17, maybe a NEMA 23, which is a motor with a 1.7 inch or 2.3 inch footprint. Over 3 kilograms torque we just talked about. I'm looking for a 6-wire motor, though I might be able to use a 4, and I'll talk about that in 1 second. And I'm also looking at a limit based on the amount of current I want to draw on that. Now, let me talk about the electrical problem for just a minute. If I use a 6-wire motor, this is the schematic of a 6-wire stepper motor. You've got the 2 coils that need to fire in sequence. With a 6-wire, I can provide a voltage on the common and short either one side or the other to reverse the motor. With a 4-wire motor, I don't have those central commons, so I need to actually reverse polarity. So if I have a 6-wire motor, I can actually use a very simple driver that would take me 5 of these packages for a total cost of about $4. Versus if I do 4-wire motors, I need an electronic interface that's capable of reversing polarity. So that would nominally be the L293D packages. So that would give me almost a $30 cost. So there's a big difference between cost on driving a 6-wire versus a 4-wire motor. But if I can't find enough price break, that might be worth looking at. So just kind of oddball, it's about $4 per motor to deal with that. Now, if I actually go start looking at motors, first thing I did was a general search. This is for 12-volt stepper motors. You got a broad variety of things, price ranges all over the map, but it does give you an idea who sells them. One of the places I turned up was Stepper Online. You can see a little bit of an idea here, the range of motors. 40. So there's a motor into the range, so it's about $12 a piece, and that's only a 4-wire motor. So there's a 6-wire at $10, a little bit low on power, so there's certainly some choices here. The other place I actually ended up looking was at Circuit Specialists. They had a variety of motor sizes. Let me start with the 23s just for frame of reference real quickly. Now what I did find when I looked there, and these tend to vary significantly, I've got about $10 for an 8-kilogram 6-wire motor. So theoretically, that guy is for $9 is not a bad choice. Let me go back to the NEMA 17 motors, which is what I actually ended up buying. The motor here at $10.15 is pretty much the motor I ended up buying. Now the thing that was interesting is I bought 10 of these motors in the summer of 2018, and they were about $6 a piece at that point. So the prices vary significantly. These are standard Chinese products. As you look around, there are some good prices down here. It's a little bit smaller, but at that price, unfortunately, they're out of stock. So the question is, how long do you want to keep looking for motors? Let me go back in and look at the specs on this guy a little bit. Now, unfortunately, what you're going to find is this is their specification. And it doesn't say much in terms of, it tells you holding torque. The motors do tend to do that. But there's nothing else here that really tells me either how fast I can turn this motor or how much power I can get it to raise with. If you look at the product specification, all it really is mechanical layout. Nothing new on that page. So if I look at that part number, just did a general Google search for it, and there's the one I was looking at. Of a lot of variety, you look at the Amazons, you look at eBay, a lot of places. You may be able to find them cheaper, but yeah, how much do you trust it? It's a hard question. But again, what I ended up with was this NEMA 17. So let me go. So that kind of drove me to where the motor descriptions were, the electrical interfaces. One thing I did find, once I got a motor in hand, according to the drawings, the black and white were going to be the two commons. I actually found the black and the white and yellow were actually the two commons. So be a little bit careful. These are kind of commercial grade, hobbyist kind of category items. Now, if I go back in and look at the implementation again, this was kind of a picture weighing the collective set of rams. This shows the mechanical connection. The motors are on the side here. This is the connector on the motor, and there's a 5 millimeter shaft on the motor with a connecting device that connects the motor shaft to the 5/16 rod. I'm using the blue tape here as a means of increasing the diameter so I can basically trade off a little bit of torque on the motor for the speed on moving it. So I increase the radius, it takes less rotation, so it takes less time. The collar here on the end catches the end of the black cord and allows me to position it both for the height on the weaving shaft as well as the position on the rod. This kind of shows where those black threads just feed straight through the holes, as well as the overall spacing, which is where I got the .42 between them. From that basic spacing, I laid out the two sidewalls with the motors. Let me look at how I did that for a second. So this is the right sidewall that has the electrical connections. So what I looked at is I'm using a NEMA 17, so I've got 1.7 inches cross section square for the motors. So I used a 2-inch increment, and the green lines here represent how far apart the weaving shafts are. So I wanted one of the rods above each one of those shafts. So the open circle here would be the motor on the other side. Here's a motor on this side, and you see the center circle where those rods are spread across. The green lines here are limited by the loom I'm using. The motor positions vertically is determined by the size of the motor. That would be the 1.7 inch. If I used a NEMA 23, then I'd probably use a 2.5 inch increment, and the whole thing would just be a little bit higher by that extra increment. So that gives me the basic layout of the motors. So from that I cut the sidewalls. The one other screw on the bottom here you see is actually the one that goes through the sidewall of the loom. It's the only modification to the loom, but that holds the Dobby head onto the loom mechanism itself. Here you can see a little bit different close-up view of how all the rods go through that would be the left sidewall, looking at it from the back side. So I can see where the threads are connected, the diameter increasing blue tape, and then I can see, when I look at that below, the thread goes through, the same feed through on the original cords from the loom, ties to the same mounting point. So I've now got that in place. Now the one other thing I had done on these is the rod itself is 5 millimeter, it's a 5/16 rod, and I'm actually using an oversized or a 1/4 inch collar here. The reason is the threads, the black thread down is going to go through that loop, and that's going to be held in place by that, and it's not moving too fast. The fact that it's off center is not a problem. So this is the overall view of the front loom, the front of the loom, the side where all the electrical connections in. The back view, that's particularly different, shows there. This is the collection of the electronic parts. The Mega 2560 is it's a healthy, good-sized processor. Using a little Mega 2560 prototyping shield, which is just the bare board. I've then populated that with sockets and the ULN 2003A driver chips that would actually handle the relay motors. And then that physically sits just inside. And the box on the top of the loom, just in this area, is where the electronics are mounted. The rest of the wiring for the other side of the motors comes in, the ones from this side over here. So I've then got the foot switch connection, which is just a foot contact that tells it when the shafts should activate. USB connection to the processor and from the host computer, and a power supply connection. And that's really what's happening here. The two bottom files here we looked at very briefly. Those actually are what I use to feed to the laser cutter. The red are the cut lines. The rest are really just pretty much references. So I had saved those as SVG to the laser cutter. They could be done with the standard template and probably just using straight round holes positioned reasonably accurate, because there's a little bit of tolerance on where the motors need to be versus the rods. Okay, let me spend a few minutes talking about the software and the electrical interfaces here. So I'm going to go from this picture. I had mentioned earlier this overall PowerPoint pitch and the Arduino source code are both sitting at the quickdrawweaving.com website under a tab for other projects. Let me kind of start with the software here for a minute because it explains kind of where things are going. Hardware connections on the Arduino. Lines 0 and 1 are hard-coded for the USB interface, so I kind of ignore those. I chose to connect the foot pedal on line 13 because it's a convenient pin with the ground right next to it. And I've got a close-up version of that here. So if I look at the blue and black lines here, just connect to the two contacts for the foot switch connection. That's a pull-up input line, so whenever a short occurs, it pulls that line low. So that takes care of the foot switch. So the Arduino itself is actually going to draw power from the USB host. The motor power is coming in through a DC connection here. The plus side of the DC connection is going to connect to the yellow and white wires on all 8 of the motors. And then the 4 other wires off each one of the motors are going to connect to the drivers. So when I go back to the source code, what this is showing me is for each of the motors, this is the pin-out sequence. So for motor 1, it's going to be driving from pins 14, 15, 16, 17. Motor 2, 18, 21, 20, and 19. You'll notice the number reverses. The reason for that is so that the motors are actually turning in opposite directions on left and right, so that the shafts are all rotating the same direction. That was the easiest place to do that. Now, what's actually happening here is where I pick up pin 14. Pin 14 is going to be one of the solder connections in this region of this board, and that's real fine. It's the yellow wires that are soldered on the back. It goes over to a driver, and if I look at the driver schematics, pin 14 on the Arduino board feeds into pin 1 on the first driver. The pin 16 is its output, is then going to connect the red wire to the first motor, connects there. So actually the connection sequence that I found works is red, green, blue, black for the first 4 connections. So Arduino pins 14, 15, 16, 17 would connect to the 4 inputs, to the 4 outputs to the motor, and they continued assigning that way. 7 pins per times 5, so I've got 35 driver channels. So for the first 2, I used all 7 of the inputs. For the latter 2, I used 6 of the 7 inputs to spread the load a little bit. I just assign those pins sequentially as you go through from driver 1, pin 1 through 7, to driver 2, pin 1 through 7, and so forth, to motor driver 1, 2, 3, 4, second motor 2, 3, 1, 2, 3, 4, and so forth. Now so that takes care of the majority of the wires. The only other wire we have to account for is the ground wire here. So there's actually a ground connection up in this area of the board. You can't see it here. That connects the ground wire from the digital, needs to connect to the ground on each one of those driver chips. And I now have pretty much all the wiring needs to be done. So that's like 32 wires off this edge of the board that are all the motor control lines, the foot switch is coming in here, and the ground line. So that is pretty much the electrical interfaces. I did use a power supply I had available. It was an old printer power supply. It was about a 3 amp, 12 volt, which seems to be enough for what I'm doing. Worst case, it could take 8 amps. It's not turning for that long. I have not had any problem with that. So you can get as healthy a power supply as you want to there, I think. Let me go back in and look at the code a little bit more detailed. The parts that are important that you may have to play with are a couple of lines here. The motor delay is controlling the real time. That's microseconds between steps. So this would be about 1,100 steps per second at 900 microseconds delay between steps. That was a number that if that number is too small, the motors aren't going to turn. If it's too slow, people complain about one thing I have found, if you get into a gray zone where the motors take more time and power to raise the shaft than they do coming down. So if that number is kind of in a gray zone where it's a little too small, the shafts will raise slowly and then go all the way back down and then kind of look like they're bouncing back up again. So if that happens, that tells you that number is just a little bit too small there. The other number that is useful is the shaft up. What that is how many steps it takes to raise for the full shaft up. It's 8 steps per times 170 cycles. I did it that way just to keep track, just so that when it gets done, it's only got one coil on rather than multiple coils. So that number kind of needs to be adjusted to where you get the shaft to the upper edge. Other than that, most of the code is relatively straightforward. The basic motor control package there controls which motor step. For each motor, it handles the I/O pins to sequence through and rotate the motors. And it keeps track of which motor is in which state, whether it needs to go forward or backwards and so forth. The serial commands are fairly simple. I did not use any standard Loom interface for the simple reason that's all proprietary data from each one of the Loom manufacturers. So I defined a generic sequence. I just send it a number from 1, 3, 5 if I want the shafts 1, 3, and 5 raised. Then when I put the foot switch, it's going to actually raise those treadles. When it's done, it will send an advance back to the host. And the only other command it really responds to is a question mark, at which point it will respond with an ID string that tells it it's a generic Loom or whatever you want to do. And that pretty much is what's there in the software and how it sets up. The initialization here goes through and sets all the I/O pins for the motors, goes through all of the motors and initializes each one of the control pins to an inactive state, and then sequences. It's slightly weird here because otherwise the motors were actually starting to move on the initialization. This is where it actually sets the input pull up for the foot switch. In the loop, it just monitors the serial inputs, so it tells it where to go, and the foot switch button so that it actually moves and everything else happens underneath there. So that's kind of the electrical and the software interfaces for a generic Dobby interface. Thank you now.